I want to ask you something before I start because I want to know like how many of you actually want to do theoretical physics, you know, as the PhD or graduate study or something like this. Not particularly like string theory, but like I want to just get an idea like how many of the applicants actually want to do, you know, higher studies in theoretical physics. Can you guys raise hand? Uh, all right, it's quite a good number, I would say. So I believe most of you guys are upper 100, right? No? Yeah. Okay. So could you guys follow the last lecture? Good. Or did you guys stop them like following the lecture? Or you guys got lost in the middle? No answer. Uh, I mean, there's a problem of doing string theory or like IoT theory. Basically, you need to have a lot of backgrounds. Um, and you need to learn it quickly because time is finite, but the background knowledge you need is kind of finite. Uh, so starting with that, okay, I will start again from where I stopped yesterday. Um, so please ask me question, and I think I don't know. You guys say the other in the back, or it's easier for me to guys come forward. You know. Anyway, if you guys are comfortable, get the spine. But please ask questions because and get ready to for the school main school, right? I mean, we got to input me and Rhetoric has gone through some very little stuff on string theory like last 2 days. But I think you understand that it's a vast subject, right? And it's an incredible opportunity for you guys. Because when I was in undergrad, I would die at a school like this, but I never had, right? So, so I want to thank the organizer one more time before I start, because it's amazing school day. Yeah. Okay. So let's go. Uh, so remember the action that we took, the Polyakov action, right? So it was kind of like this. So we choose some thing called conformal gauge. So you remember there were some gauge choices that you had to make, and after the gauge choices you made, you more or less add some solution like this. Oh, and we talked about closed string or open string. I just want to show you how it arrives. Okay, so this was the action, and it's a quite good-looking, nice-looking action that you can handle. So what you can do, so you have to make sure that under any such deformation like this, the action remains invariant. Yeah, right? Cool. So, or in other words, so under x mu goes to x mu plus del x mu, you will have under this, so the s will also become like s plus del s mu, right? Um, Del s basically, and the del s that you have will have a formation like this. So please, I'm skipping the state, of course, but please do this steps by yourself. And after the talk today, I will be available please ask me about references. Yeah, I didn't give you guys that much yet. So So just to recap that we had a string wall shape like this, right? Uh, and basically this is sigma this way and this is tau, right? And so it's a finite like length like this. So we can call this guy sigma equals to 0 and this guy sigma equals to some pi or whatever. Something, right? So and this is basically the action of this string. And you have to make sure under the coordinate solution of x mu, the variation of the x mu remains 0, right? I mean, it's a common step people follow in usual everyday physics. So we can see that there's a couple of ways to uh, make this guy vanish, right? There are a couple of ways to make this guy vanish. So what can you do? You can first of all make a periodic condition, and the periodic condition is basically x mu sigma plus pi at any tau is given by x mu sigma and tau, right? So this is one of the condition, the periodicity condition, and I think you will agree that under this periodicity condition, this del S becomes identically 0, right? Any question with that? Do you agree with this? Because if you make sure that at sigma goes to 0 and sigma goes to pi, x mu's are the same, then they identically vanish, right? So this is the condition, and that's how it's called the closed string. So basically, you had a paper like this, and you make sure you audit like this. That's it. So you identify a point at sigma goes to 0 at sigma equals 5, and that makes sure that the variation of the action is 0, right? But you can also choose some other boundary conditions. This one is periodic, which gives rise to closed string. But you can also make open string by putting Neumann boundary condition. And what is Neumann boundary condition? Neumann boundary condition is this: del sigma at x mu, which is, we write it as x prime, is 0 at sigma equals to 0 and pi. So this boundary condition makes sure that the variation of variation x mu pi at both ends are identical. Okay, the x mu itself is not identical. The variation of the x mu is identical at those points. It's sigma equals to 0 and sigma. Okay. So this is called the Neumann boundary condition, and that actually makes sure that the variation of the action is 0 under the transformation x mu plus del x mu. Cool. And finally, we have Dirichlet boundary condition, which says that del x mu is 0 itself. The variation is itself 0 at sigma equals to 0 comma pi. Yeah. So under these two choices, which is this one and this one, these two choices make sure that the variation is itself zero under the coordinate transformation x mu goes to x mu plus del x mu. So these are the three choices that you can make for solving the action of the string. Yeah. So do you guys have any question or conclusion about that? That these are the couple of choices you can make. You can make more crazy choices, but these are the most physical choices that you can make. Okay. So just to give you a picture, so my drawing is very bad, by the way. So forgive me. Uh, so when there's a Neumann, so the Neumann boundary condition, it means that oh, so this one is kind of like the Neumann boundary condition. It just says that del sigma, the variation of the differentiation, like this condition, this condition is basically portrayed in this picture because it says that the part is it's like perpendicular, right? Like a string is ending somewhere. It's an open string, like just like open string is like spectrally straight, nothing else, and it's ending somewhere, and and it's perpendicular to somewhere wherever it is in. Okay, and that's why you can see they are perpendicular wherever they're in. But the string can move anywhere on the surface, right? The string can move anywhere on the surface. Still, they will be perpendicular wherever they're in it. Cool. And then you have another boundary condition, which is the Dirichlet, and this just says that 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 it speaks somewhere. Like you make sure that wherever I put the string here, and it just speaks there. It cannot move, but it doesn't tell you that it is perpendicular to wherever it is ending. So so we found out that the string we actually quantized there, and last time we saw that yesterday we saw that when you quantize space, there are like lot of particle images, right? Like graviton, we saw that. But what is also surprising that actually the open strings on the coast, the open strings are ending somewhere, right? Because you are giving these boundary conditions at somewhere at sigma equals to 0 and sigma equals to pi. So they are basically ending somewhere. So people understood string theory or discovered string theory long time, like 1980s or something. But took like 10, 15 years for people to understand this, that strings end somewhere, and that's what called debates wherever they end. And it took someone very brilliant between us, Joseph Optinsky, who made this wait, I cannot. And from P to D minus 1, I take digit. Yeah. So whenever you choose a condition like this, I'm very bad in this thing. Okay. Whenever you choose a condition like this, it just means that the strings are ending on the on some surface, right? On some hypersurface. And because we choose this. Okay. And that's the very basic or the most trivial thing I could say about the brains. Uh, and now I will go yesterday later on time and remind you about type B and type 2 asynchronous and show you that how these debates actually arise in those theories. Okay. So for now, do you have any question for me about this boundary condition and everything? Yes, please. Tell you. Any more? No? I mean, if you guys don't ask questions at some point, I will force you guys to ask questions. Yeah. So careful. Yeah. Okay. Cool. So I will now take you back to something very basic. Yeah. Which is Maxwell separation. Sorry. What's the question? Yes, is you just choose, right? You can make like you choose now normal. You can make everything usually or everything normal. But I give you like a most general choice like this. But you can make p equals to 0, p equals to 1, p equals to whatever until d. So I give you a general choice, but you get the pick your creditors. That's fine. Okay. I think the notation here is using the like the white per environment but condition over. No, you don't prefer anything. I'm just saying that you can. This is a hypersurface where the open string ends, right? You can either choose Neumark or Dirichlet. It's up to you. And depending upon what is the number value p is, not that I know, or really interesting. Like you can make ICTP can do something like this, but those will be for harmonic states. The action I wrote here is the bosonic string action, but you can have fermionic string as well. Like instead of bosonic coordinate x mu, you have a fermionic coordinate and fermionic string. And for them, you can give some other weird boundary condition. Yes, but now not right now. Um, it just means that whenever some the yeah, whenever you give Neumann boundary condition, they they end perpendicularly to the hypersurface. Okay, so I will now go back to some Maxwell equation, and I hope that many of you are familiar with the differential forms. Okay, so just to remind you that this is two of the Maxwell's equation in the differential form notation, right? And then you have another one, which is kind of like this. Yeah. So right now, we are considering four dimensions, but very soon I'll go PG and for a string notation. But I just want to remind you that this guys means that yeah. So are you familiar with these two equations? So Maxwell invented 100 years ago. Yeah. So you can write in the differential form notation, and basically there are some advantages that you can get. So for example, the electric charge when retaining this kind of okay, basically this, right? So and you can also define magnetic charge, which is like which is like this. So F is a two form, right? So F is basically a two form, and to integrate the two form, you need a S2 or ICI. And then basically what you are doing, you are surrounding the charge with a flux, like with a sphere, right? And you're just implementing Gauss's law to understand what is the electric or the magnetic charge. So in the most usual case that we study, uh, there is only electric charge, right? But actually there is no reason to believe that there is a magnetic charge. And in string theory or high energy theory, we always deal with magnetic monopoles and stuff like that. So, I will come back to this right now. So this is how you actually define the electric charge and magnetic charge with respect to the two form, right? So just to remind you that whenever you had a point particle moving in time or space, right? They're moving in time. And let's say this point particle is charged. So I write a four-dimensional, I write this is the action for the Maxwell equation, right? And the Maxwell equation, the photon, the charges is coupled to basically a point charge. So this part I want you to focus. So remember the Maxwell equation has what? A mu, right? It has a vector field. And this vector field is a vector, right? So it has one leg in the space there, right? And this guy is coupled to what? A point particle. And the point particle moves in the space time, right? And it just creates a curve like this. So whenever there's a point particle, the only way the point particle can get charged is with respect to this gauge field NE, right? Do you agree? Like the electron, which is a point particle, is charged under the gauge field, and the electron moves in the Bob line, which is a one-dimensional thing. This guy is coupled to the gauge field, which is also a vector. Cool. So let's meet a point. A point particle which is described by a word line naturally coupled to one form, or in other words, a mu, right? Gauge fields. Now let's talk about you have any questions, or you're just like just relaxing because you know this already at the so a string is like what? A string is just the string, right? And when it goes to the space and time, it is a wall sheet, right? So a string or described by wall sheet naturally couples to what? Can you tell me? Like the point particle couples to a vector field or a one form. So wall line couples to a one form. So the string, which is a wall sheet, couples to what? Two form. Very good. Okay. Cool. Uh, right. Let's move on. So the string, which is described by wall sheet, couples to a B2, right? And I'm gonna remind you right now what we did yesterday. So we saw what are the vector, the bosonic spectra of the string theory, right? It had a so whenever you both type 2b and type 2a had this, right? It had a G mu nu, D mu nu, sorry, B mu nu, and phi. So the string is getting coupled to what? This binary. And the string is charged under this DDD. Okay, cool. But do you remember that in the type 2B theory, we had what? In the type 2B theory, we had F cos F C0 C mu nu to form and C4 mu nu rho sigma a 4 form, right? Yeah. And the type 2A had what? It also was the chiral, right? And then you have C1 mu and C3 mu nu rho. So this guy is coupled to string, the fundamental string, or some people call it F1 string. Don't ask me why they call it F1. I guess they can also string being a one-dimensional object and the FP fundamental. So people around that time had some crazy names. I don't know who gave them, but I don't know. Look into the books. I don't know who gave them these names, weird names. But the point is that these fundamental strings are charged under the B2. But we also have this T naught, C mu nu and C mu nu rho sigma, right? And these are all forms. Yes. C naught let's go. Thanks. Yes, of course. So we also have this higher form fields, and I guess you can see where I'm going. So the F1 string, the fundamental string is coupled to a 2 form. So let's take this guy. Yeah, this guy is coupled under something, right? This is true, and this is solved D1 brain, and this is coupled to this D1 ray gives rise to the charge. Or the charge in the D1 brain is given by this guy, right? So let me give you something. So I tell you that type 2A has stable DP brain with P being even. Yeah, I will show you how it arises, but let me just write it first. And type 2B has stable DP brain with P being odd. Yeah, cool. So whenever we have n, oh, yes, and but the very smart. That's very good. I will put them later. I mean, it just means that you can have P odd in the type 2A string, okay, type 2A string theory, but it is not stable, meaning that the charge is not conserved, so it will decay. This is what it means. So we have n form gauge fields. Cn in string theory, which is fold electrically to a p brane, where n is equals to p plus 1, as my good friend. But you are 30, 40 years late. If discovered it long ago, unfortunately. I just want to make one comment, is that whenever I write p brane, it is actually a p plus 1 dimensional. Sorry. Yeah. Okay. I can write those actions, but I mean, at this point, I think it's gonna be too much for you if I write this action. I mean, you have to derive them or look into them before. Otherwise, it's too much. But I want to make one more, a couple of more comments. Is that so? This coupling that I'm talking about is what? This is basically it's coupled by electrical charge, or in other words, the charge which is given by some formula like this, right? Now we will see that that it is also these higher from fields are also magnetically charged to some rates. Okay, cool. So let me start. So we had this B2 field, okay, and the field strength of this B2 field is given by what? dB2, which is so I hope you guys know exterior derivative. So it's a two form, and I dig it with a D, and it's gonna be what? Can you tell me? Three form? Cool. Yeah. So it's a three form, and let me just for completeness, I give you like D equals to 10, the dimension. And if I take the Hodge dual of this three form, can anyone tell me what is it going to be? I tell this H what? Anybody? No? If you have N form in D dimension and you take the Hodge dual of it, it's gonna be G minus N form. Okay. So in this case, it's gonna be H7, right? And this can be written as Da6. Yeah. So this B2 field is electrically coupled to F1 string, and this is magnetically coupled to something called NS5 brane. So this NS5 brane is six dimensional, right? Because how do you understand that? So this A6 tilde is a six form. So the only way you can couple to this guy that you have a 5-dimensional or a 5 brain basically. So we can just knowing that a BT field exists, this BT field electrically couples to the fundamental state and it magnetically couples to the NS5 brain. So without doing nothing, just doing this stable differential form exercise, we can understand this NS5 brain exists. So what is very weird about schedule that we started with just grades, right? And we quantized it and we realized, okay, we are not alone. There are like many other weird things happening. We got this aggregation objects must exist for this thing to be valid. So we now have, if we take a let's make a general exercise. We take a CN form, yeah, and this guy, of course, electrically coupled to P brain, where P is equals to n minus 1, right? We saw that here, right? And now we want to understand how, with what kind of brain this guy is magnetically charged. Is the exercise clear? Yeah. So let's start. So what we did, let's take the stereo derivative again. dCn, this is given by f what? N plus 1. Now you take the Hodge dual of this guy, it becomes what? Yeah. And this can be written as dc tilde x minus n. Yeah. And realistically, this is c tilde h minus n, which means that this Cn form is magnetically coupled to a P prime brain, where P prime is given by 7 minus n. Because it's a pure strength, right? That's why. It's a pin strength. Pin strengths are always it's a. I mean, if you make df tilde, it's do, right? That's why. So we learned that not only this P brain exists, also P. Yeah, please. Yeah, right, great. So basically, yeah, let's go there. Uh, I mean, I have not written you the action, so it's hard for me to tell you. Otherwise, I would show you. I would love to show you, but otherwise it's gonna be too much. But let me write some stuffs, and then you can tell me that you are okay, right? Cool. So we what did we have? We had a C naught, C2, C4, C1, C3, right? So let's just write them, and then I use these two formulas, right? So I have a C1. Sorry, I have a C1. So if I have a C1, I use this guy. Okay, let me just write first everything. C2, C3, C4, and then I also have C0. This C0 will give rise to something very weird. Let me stress that guy thing. And the guy who actually figured this out is coming to the winter school, Ashok Sen. So ask him those things. I even don't know what it means. So don't ask me this. So this C1 exists, and C2 exists, and C3 exists, C4 exists, C0 also exists, right? From here, we know that. Yeah? So this guy is electrically coupled to what? Just using this, I can tell that it's electrically coupled to a D0 brain, right? And this C2 is electrically coupled to 2 minus 1, a D1 brain. And C3 is electrically coupled to what? A D2 brain. A C4 is electrically coupled to what? Just use this formula. A D3 brains. Yeah? And the C0 is electrically coupled to, unfortunately, something called T minus 1 brain. Okay, let's omit that for now. I will come back to it later. But coming back to this gentleman's question. So it is also magnetically coupled to something, right? This D1. And that is going to be 7 minus 1 is D6. 7 minus 2, D5. 7 minus 3, D4. 7 minus 4, D3. And 7 minus 0, D7 brain. So we had D0, D minus 1 to D7 brains exist in string theories. And because, let's see this, just give me 1 second. So I marked the type 2B ones as C0, C4, and C2, right? So that's why in the type 2B, you only have brains which are identified with odd. So that's why type 2B, type 2B has DP brain, T being odd. And obviously, the other words are even, and you know why in type 2 ATB, between DP brain and PB even. So as my blueprint again asks very interesting questions, which is anti-brain. I come back to you, right? I come back to you on that. But do you agree that these D brains must exist for string theory, because this higher form field exists in string theory and they are charged under something, right? And the only way they can get charged is so that these higher dimensional objects exist in string theory. Yeah. So string theory is not really just a theory of string. It has all sort of high dimensional objects moving around. And these are very highly massive objects. Yeah. And the number go to action, if you remember the number go to action, it was given by basically, just give me 1 second. Right. It was given by, sorry, it was given by minus T d2 sigma minus z gamma, right? And gamma alpha beta was del x mu, del sigma alpha, del x nu, del sigma beta, and eta mu nu. But the important part was that alpha and beta takes value 0, 1, right? This was the number go-to action for fundamental spring. And you can write the de Bruijn action in the similar kind of way. So I give this P so that you understand it's a P Bruijn, dP Bruijn, sorry. And it is basically given by ICTP dP plus 1 sigma. Yeah. So basically, the number go-to action was for a wall sheet coordinate. And now you see that for the dP Bruijns, we obviously have the generalization for the number go-to action, and this is the action for P Bruijn. Yeah. Okay. So I have gone a lot for now. Do you guys have any questions? She's it's the DBI action. So DBI action is when like to couple to this number of actual sum caches. That is a DBI action. Any more questions on this? No? So should I go ahead or should I stop here? It's up to you guys. I don't want to over stress you. What do you think? Should I stop here or should I go more? Because I don't want to go if you guys are stressed out and don't want to listen more. Please tell. We can go on? Okay. Oh. So for now we have seen that we have these D Bruijns in string theory. But one of the research goal of string theory, which I said the last time, is to understand or to derive this sorry. Right? So this is the FRW metric. And some particular interesting metric is when A of t is given by exponential h times t, right? So this is called, again, Decider solutions. Yeah. I spent the last couple of years of my life understanding these Decider solutions in string theory. So just to tell you something very interesting about dark energy is that the dark energy is something very interesting in the sense that when you have the density and pressure, if you take the ratio of it, for ordinary matter, it always some positive number, right? Yeah, like if you give pressure to the object, the density always rises. Yeah, cool. But what is very weird about dark energy, or in fact, this kind of basic solutions, is that if you give it pressure, the density decreases. This phenomenon actually helps us to keep going the exponential expansion that we are seeing in our observation universe right now. So one of the um, goal of string theory initially was to understand if we start with some 10-dimensional manifold and we have some compactification like this, which is a compact manifold. Yeah. The question is, let's compute the scalar curvature of R4. Yeah. What is this R4? Is it R4 is equals to 0? Is R4 greater than 0? Or is R4 less than 0? Yeah, it's very interesting to ask, right? Like, because at the end, we have to compactify everything, right? And to get a universe that we see, the curvature will be positive because we don't begin a negatively curved space. Although in our field is string theory, most of the people somehow are very interested with area safety, area safety correspondence, but this area space has R4 less than 0. Yeah, but to get a observable universe like we have, we want this guy. We want this side. Yeah, and I will just quickly derive something very quickly. Um, right, like to just to understand, if we want to have R4 greater than 0, what kind of quantity? Because we always have to maintain this guy, right? This is an equation, and the string theory is a 10-dimensional theory, and you have to solve this Einstein equation, right? So you have several constraints when you are doing string theory. Is that okay? You have a string theory that you have to solve this Einstein equation, and you have to get R4 greater than 0, right? Cool. Now let's take a space time like this. So this G mu nu is basically your M4, and this guy is your M6. But this kind of compactification is called warped compactification. And we have a local expert here, like he, who works on this kind of compactification. And his boss, Chikoli and Kevedo is coming. They also worked a lot on this kind of compactification. And they claim that in their way, they can get this. Okay? I'm not very sure about that. I'll show you why. So we had this MD, and then you have M4 cross M6, right? So you can compute the Ricci tensor for this kind of solutions, and you get, sorry. And then using Einstein equation, you can write this guy. So these mu's are the space-time indexes, and the small a is the index for this guy, and mu is the index for this guy. Yeah. So in order to get R4 greater than 0, the invariance that you have in string theory must admit something like this. Yeah. And one can show, using the classical ingredients of string theory, you cannot satisfy this solution. Which one? I mean, I can say, I mean, it's a kind of, you have to do some work. I mean, I mean, so just looking here, actually, is just using this guy. Then you can take the trace of this guy, right? In the left hand side. If you take the trace of that guy in the left hand side, you will come into this guy. Yeah. I can give you the artifact number of him. So this is the famous no-go theorem by Gibbons, Maldacena, Nunes, and this no-go theorem actually tells you that in order for the curvature of the space-time to be greater than 0, you need to satisfy that condition. The problem is using the classical components of string theory, it is impossible to satisfy that. So what are the quantum convolution of string theory? We don't know. But it's ongoing research, and many people claim that it is possible to satisfy that the PDU is not changing. So it's ongoing research, and Mission Chikori and Quevedo are working on that. So please ask them questions on this if you're interested to work on string cosmology. And with that being said, I think it's a good time to stop today because I did see a lot of lost faces. If somebody has some questions, please ask me. I will be here for a couple of minutes. Yes, please. The new is index for the external direction. That means M4. And M6 is the MM1. Yeah. So, okay, let me just give you our tag number. It's the best. Yeah. Tracking number.
Yeah, it's a BRI, the same pin as a BRI with an opposite charge. So you saw he was showing how fields are charged under how brains are charged under some field. So if you get the opposite charge, I mean the same tree, that is an empty tree. It is called Arab, if you want to look up. Actually, we had a paper a few months ago where we were it was an extension of the very old paper by Fernando Mabu, who's our team here. They it gave rise to iteration. So that traction in the same way. So the same way we had an extension, you might want to check that out. Sorry for the small advertence. Please.
Yes, the existence of demons actually break happens. That you already have. I can talk about it, but it's gonna be a long that. So the there are two instances as A equals to 2 superset. Okay. And N equals to 2 supersymmetry, I can mention you can count how many supercharges you have. And each brains actually break out of the super because it breaks some of the lines in the
I have a question. It might sound stupid. I'm trying to understand it. Did you have a logo serum so you're not replace of the original question for that to be greater than TNN, which is for higher level, for this way considered it's what does this physically imply? Because like for generic the universe, right, we have different dimensional and why you just said that essentially depicts the content of the universe, right? That is larger than TMN. For us to have the figure, which we do essentially, right? Because we are
So that's a problem. Like maybe there is extra keywords, but it might not have any string theory completion. We don't know if string compactification gives rise to the decitor. So of course, my friend Rakin and his collaborators been playing that they have done it, but I'm not very sure
And then so because I look at those stuff. But this seem like potential bias.
Yes. Again, if she kills the report of my supervisor, it's gonna be a fight. So let's not go there. On the other hand, I'm not sure like which one. It's something that we have to do research upon because it at the end depends upon the quantum formulation of string theory. Because the classical ingredients of string theory definitely don't give rise to this. But we know that this type 2 string theory is actually did not have time to talk about it, but this type 2 string theory. So there is a M theory, something called M theory, which is in 11 dimension. And you compactify one of the directions of M theory, you get type 2A. And if you do T-duality, you get type 2B. And if you uplift this type 2B, there is something called F theory, which is 12 dimensional. And the funny thing is, neither the M theory or the F theory has something called string. It doesn't exist there. So it's quite crazy that we started from a theory of strings, but the non-parametric formulation of that guy doesn't contain anything called strings. It only has M2 brains and M5 brain. And basically, Ashok Sen understood how community you can get factory. It's one of his biggest things. So asking his questions. But long story short, because we don't know the quantum formulation of M theory yet, I cannot actually tell you if this is satisfied or not. So it's ongoing research, but for the last 2 years, I'm not doing those things very much because at this moment, we don't have any quantum formulation of M theory. So maybe in the next 100 years. Yes. But I didn't tell you all. I don't know how to contact the brains. Nobody knows. Maybe you.
So if I may add, if there is an unknown or unsolved problem, it's always best and exciting for us to join the efforts and maybe contribute in any way you can. If it seems fun and interesting to you. And just to add, in the last few years, I had received few okay. What is the word which the biggest humongous discussion suggestions from Paya in the last, I think, 2-3 years. I've always called him up to ask for. So I would request you to ask him. He's the storehouse of knowledge. Just ask him anything in the school. You will have him for 6 to 7 days, and ask him today as long as you're here. So he'll help you and give suggestions on how to do things. So if you ask him anything, I have made the best use of that opportunity.
All right, we should finish it.
So with that, any questions? So if not, we can end our preschool and let's stand.
I mean, I'm not really worried about dark matter because I work in a lot of high energies. Dark matter is the particle physics question. And I don't know, like people try to do particle phenomenology with string theory. I am not a big fan of it. I'm not sure. It's like asking a question like, can you explain the water boiling in a pot with quantum mechanics, So it's kind of like a question like this. Like, if you want to model particle physics using string theory, it is kind of asking like, can you explain water body with quantum mechanics? So I don't know. But string theory has something called dinadons, and we also have something called axioms. So I believe that these axioms, people claim that they are dark matter entities, but I don't know. I don't work on it, so I can't tell you.